Okay, welcome back. So we're almost at the halfway mark, and after tomorrow's session will be only, or session 7 will be only left with what are known as classes of algorithms, adversarial classes of algorithms. Other than that, we're mostly done. And then uh, we have talked about variational models, and we have seen how to sample from a latent variable and how to use that latent variable to make predictions. So I'll give you a brief recap. Today is going to be a very light session, and we'll be doing a very fun exercise where we'll be implementing a diffusion model. And we'll try to keep this a shorter one, but you'll have a lot to take away from this. We'll see more generalized versions of diffusion models, which are more becoming more and more popular in particular tasks nowadays. So to be exact, so what we'll be doing is we'll be just a moment. Yeah, we'll be talking about flow models or flow-based models. In session 1 to 5, what we did was we did variational inference. We did the EM algorithm, we did the elbow. See in our syllabus, that's like 4 modules already covered out of 6. So score matching. Out of 7, if we get some time, we'll do some recognition parameterized models as well. So what I'll do now is so the next 2 sessions would be extensions of these model ideas. So from diffusion models, I'll come to the idea of flow models. And from score matching, I'll come to the idea of energy-based models. So this is going to be session 7. So 6 is going to be flow-based models, and we'll see what that mean. So we have seen in diffusion models that we started off from the data distribution. We kept adding noise. So we said PZ1 or PX1 and PX2, and we went all the way to P normal 0, 1. So this was the idea that we were following, and we were adding epsilon amounts of noise at every step. So it's like a transformation of random variables. So we were transforming xi plus 1 from xi by adding small amounts of noise, 1 minus alpha I plus 1 epsilon. So this was the function that we were using to convert from one random variable to the other. So today what I'll do is, so we'll stick to latent variable models and series of latent variable models. So you can see that there were a series of random variables x0, x1, x2, and dot 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 x capital T, where xt was distributed as normal 0, 1. So what we were doing in the forward process in diffusion models was we were taking the data distribution and we were converting it to a noise distribution by slowly adding noise. Today, what we will do is we will do the reverse. The idea of flow models is it is like a diffusion model where we model a function from a normal 0, 1 distribution. Say we name this as Z0 or X or whatever. Z0 is sampled from normal 0, 1. We take a function f1, we convert it into p1. We take a function f2, we convert it into p2. And we go all the way till ft, and we get the pxt distribution, which is set to be equal to the px distribution. So you can see it's the reverse. So the flow model is a reverse idea of a diffusion model. What are the similarities? The similarity is again a set of transformations of random variables. Transformations of random variables from a stereotypical distribution P of z 0. We'll see the notations as we go on. And so we go towards P of x set of transformations. So if you see this, it's like you take the normal 0, 1 distribution, you put a neural network. It's often these are neural networks. You convert it into another distribution. Again, you take another neural network, you convert it into the other distribution, and in the end, you match the PXT distribution to the PT distribution. It's very similar. So what some of the properties are, generally, we take FIs to be invertible functions. Why? Because if you take them to be invertible, the reverse process is simple. Reverse process is simple. So they like forward, we'll see often the forward and backward processes are the same, are the same operations. Okay, so we'll see why do we take that and so on, but these are the but the difference that I have is the difference from diffusion model is we try to reduce the number of steps here as we are learning arbitrary functions which could be capable of converting latent z to x directly. So we'll see one example where there'll be only one layer in the flow. There'll be one flow. You could have multiple flows, but that's a design choice that you'll be ending up. For now, you're able to understand that the foundations is what is more important. And the other thing is the ease of computing likelihoods. That is log p theta of x. So if say you have data, this is your training data, this is your new point test, this will have a low likelihood because the data model has never seen this data. And often they're used for outlier detection. Detection of points model has never seen. So, okay, so the overall goal is clear of converting latent z to x. The overall idea of flow models is very simple, is that it's again a latent variable model z, which you convert say z0 to z1 ... and you finally get x. So if you take this layer to be one layer, just one layer, you can think of this as you have a latent z and you have a function f theta and you're converting it into a data distribution. That's the idea. So in the diffusion process, you do exactly the opposite. You were converting your data to the noise distribution. But here I'm saying that I will learn a linear transformation, or sorry, not linear. The idea is learn a transformation f theta from latent space Z, or the stereotypical latents, which you can control, for example, normal 0, 1 or uniform 0, 1 to the data distribution, to data. So inference is very simple. Inference is just you sample Z from PZ and X is equal to F theta of Z, which means X is sampled from P of X. So we'll see how we do this. So I'm saying you can sample a latent and you give that latent to the model, and the model will give you a new data point. And how we are going to do it is by a series of linear operations. And before that, I'll just briefly recap what is a transformation of random variable. So this, you can see that we were saying that the underlying distribution of by manifold hypothesis says that data actually lies in a very, very low dimensional manifold. You can roughly think of this as a subspace, say 4 or 5 dimensional data. As we've spoken before, the phase data could be like the size of eyes, the skin tone, and the size of lips, and then this the face shape, amount of hair, and things. 5, 6 features can actually tell you what a face would look like. Whereas an image would have a 10,000 by 10,000 or 1,000 by 1,000 just 3-dimensional space, which is a lot of redundant information. So we're saying that from this 6 or 7-dimensional or 10-dimensional latent, we're going to take a model that will just take that latent dimension. And we've been discussing it for a while now, that you'll take the latent, you will pass it through a F theta module, and you'll get your data. And we'll see a similar concept in GANs as well. But here in flow based models, the idea is that this function F is selected such that you can actually model it like a diffusion process where you are going from one distribution to the other, and all of these simple transformations is actually leading to the final diffusion or final distribution. And one of the key advantages, as I said, that we'll be seeing that this can be used for likelihood estimation, which diffusion models and GANs are really poor at. So let's look at it, how we can do that. And before that, let's discuss transformations of random variables. Transformations of random variable. So we'll take a special case in my in ML 2024. We have discussed, for this is the GATE course. This link we have is there in my YouTube playlist. We have discussed this transformation for any function f. But since it's a specific case we're going to deal here with, we'll redo it for only the specific case where f is a monotonically increasing function. Monotonically increasing 1, 1 and onto function. That is, it is invertible. And we are saying that, say, x is sampled from px, right? So let's see what is the notation I'm using. It's okay, z. So we are going to say that, say, f theta transforms z to a random variable x, which means that you're going to change the distribution of pz to px using this function f theta. And I'm going to show you the relationship between these PDFs. So let us, for the time being, take the CDF. F of x is equal to p of x less than x. Let us just define it. I know you have already done this definition. So these are PDFs. We're assuming PDFs exist and the function f is monotonically increasing. So we're going to see what this transformation looks like. So this is p of x, the integral of p of x dx from -infinity to x, the PDF's integral. And this is the measure, the probability measure of the random variable being less than a value x. And this x is the cortex. Sorry. Let's like write down the PDF of z then. So if you're trying to write down the CDF of z, you'll get the measure of, or the f of z Let's use separate notation f of z as the integral of, or as the measure of the random variable z being less than equal to z, or the variable or the value z, small z. All right. So what we know is, we know that the transformation is given by z is equal to f theta of x. We know that, right? So if z is equal to f theta of x, so I know the random variable will be p of, so I can write down the random variable in terms of, so this is the transformation of the random variable. I just replace it in terms of x. So I'll say f theta of the random variable x being less than z. And so note, we have assumed invertibility of bijective f. We have assumed a bijective f, bijective and increasing f. So if it is increasing, the inequality does not flip. So we know that if an increasing function, so if x is less than, I don't really have to show that. This is like the measure here is p of x being less than f theta inverse z. So we'll write that down, but the idea is f theta bijective means f theta inverse exists, right? And when it exists, you can write this, you can take the inverse and get this value. So for the particular value of x, let small x be the f theta inverse of the value z, right? So I can write this as p of x being less than x, right? The random variable being less than x, which is nothing but the integral between minus infinity to f theta inverse z, right? Px of x dx, right? So this is, we know that this is my small x. So therefore I can write this in this form. So this is my f z of small z, right? So so I get this equation that I get for transformation, right? So I'll just, for a moment, I'll just show you. Say if x1 is less than x2, so we know for monotonic functions, so this is a monotonic function, this is x1 is less than x2. So clearly f of x1 for monotonically increasing function is less than f of x2. Right? So this is also known to us. So even if you take a inverse of any function, and all of these values won't change, the inequalities won't change. Therefore, inequalities for monotonically increasing functions don't flip. And here, even here, you don't even have that inequality. So so your value z being less than equal to some value z. So if you have that value z1 here, z1 here, and z2 here, so you will have f inverse and f. So if this is your value z1 and this is your value z2, your f inverse is always going to be, if z2 is greater than z1, your f inverse is also going to be the same sign. z2 is equal to x2 is also going to be f theta inverse of z1, which is equal to x1. So this, even the inequalities for the inequalities don't shift for the inverse functions. That's what I wanted to say. So no worries about taking f theta inverse in the probability measure p, right? There's no worry in doing that. So okay, once I do that, I can do one thing. So as I have defined this, is from minus infinity to z, or small z, pz of z, right? So this is what I'm doing is, this is for a 1D case. So if you're asking, so why suddenly this is for a 1D random variable. variable, and we will convert it easily to a random vector where we'll be having d dimensions as in images and so on. It's not going to be a problem. So minus infinity to x f theta inverse z px of x dx. So if I take the derivative on both sides with respect to z, if I take the derivative with respect to z, what will I get? Right, I'll get by Newton-Leibniz formula, the value is just put into the PDF. Pz of z is equal to px of, you put the value here, f theta inverse of z and dd z of f theta inverse of z. Or this can be written as pz of z is equal to, of the random variable z is the PDF of x. This is nothing but x. We know that f theta inverse z is x because it is his injective versus a bijective function. So you can take an inverse, and this f theta again is like x dz dx dz. Right? So this is the popular transformation of random variable formula. Transformation of PDFs. Okay. So now we have seen this, and now what we can say is, so even for a negative or a decreasing function, we will see the same value, but that is not important. So what we will see here is for ND, for n-dimensional space, P of z dz is equal to P of x dx dz. The mod of this, because for decreasing functions, you would have a negative sign and you would just take the absolute value there. For ND, this is just the determinant. So P of z dz for ND analogous, n-dimensional analogous equation is given by Px of x, dou x, dou z, the Jacobian matrix, the determinant of the Jacobian matrix. So you can see one thing that we will assume for ND, for n-dimensional space, for a Jacobian determinant of a Jacobian to exist, dimension of x should be equal to dimension of z. This is another similarity for determinant of Jacobian to exist. Right? So we know what is a Jacobian. So if x dz, if x is equal to x1, x2 dot 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 xt, and z is equal to z1, z2, this is the matrix of all the partial derivatives, right? So we done this in multivariate calculus, where we'll take d of x1, take the derivative with z1, x1 with respect to z2, and all the way to x1 dz similarly dx2 dz1 and dxd dou z d. So this is the product, this is the matrix, a d cross d matrix of all the partial derivatives. And you take the determinant of that for a 1, 1 function, 1 on f, 1, 1 f. So f here, again, x to f theta of z must be 1, 1 on to increasing. And what does this say? Invertible or bijective. This has to be a bijective function to have this, all of these properties defined. So good. So now we have got the background or the framework on which we can work. So the framework is, if we have to write down the lemma, which we proved just now, lemma is if f theta is a bijective function, then, so it does not have to be monotonically increasing, though it just have to be bijective because we're taking the determinant, which is always the absolute value. Okay. Of course, the absolute value of the determinant is what you'll be taking. So I'll just put a double here. So the absolute value of the determinant. Right. So if f theta is a bijective function, so what we can write is we can write p and x is equal to f theta of z such that x is sampled from px, z is sampled from pz. Then we can write px of x is equal to pz of z dz dx, the determinant of this. And we'll be extensively using this formula in our understanding, right? So let us now come back to normalization flow model. We'll do what is called as a normalization flow. This in this case is a general case of a diffusion model with a time convention where they start from a stereotypical distribution P0 and move towards the data distribution ZT, which is represented by PFX here. We start from a stereotypical distribution P0, that is Z0 is P0, and move towards ZT, which is a set of simple reversible transformations, a set of simple reversible transformations. So it's very similar to a diffusion model again, this normalization flow, but what we see is the initial or the convention, the first state where you start sampling from the time equal to 0, you have the stereotypical distribution or the normal 0, 1 distribution. At time equal to t, you get the data distribution, which is just the reverse process, reverse notation of a diffusion model where you had the noise, the data to be the time 0 per distribution, and at the time t, you had the noise distribution. Okay. So we will define that every transformation Zi minus 1 to Zi is given by Fi, right? So this is the inductive process. This is what I'll do. So I'll get Zi is equal to Fi of Zi minus 1, where Fi could be a neural network. Okay, where Fi could be a neural network and it will convert the previous time point to the next time points distribution. Okay, so now if I do that, so I can write that ZT or Px, ZT or my X data is f of t, z of t minus 1, right? Similarly, z of t minus 1 is obtained from z of t minus 2 using f of t minus 2 or t minus 1, right? This is what you're going to use. So again, by induction, I can write this as f of t minus 1, z of t minus 2. And I keep doing it by induction. This is equal to f of t minus 1. And you make all this composition all the way to f1 of z0. And this is the stereotypical distribution. And what we know is you could also invert this entire thing. This is the caveat is Fi's are easily invertible, right? So you can easily invert these FTs. So how can we, so if we had to write Z0, we can write this as FT inverse of X. So I'm just taking the inverse taking inverses. So FT inverse, FT minus 1 inverse, FT minus 2 inverse, and all the way to F1 inverse. And you get the stereotypical distribution, right? So this is the inverse map. This is your ZT. This is my ZT. If you're wondering how did I get that, reverse, take inverses. Take inverses on both sides from t to 1. Right? So you'll take, so if you're wondering how did I do that, so I'll take ft inverse zt is equal to ft inverse ft, and you have the rest of it. So as soon as I have ft inverse ft, this will cancel out and I'll have whatever was inside this. So I'll have ft minus 1, ft minus 2, and all the way to f1 of z0. And then again, you can take the inverse. Again, you can take inverse of ft minus 1 inverse, and I'll get ft minus 1 inverse, and dot, dot, dot. So this will give me by induction. Correct. So this is not a difficult thing to do. So now what we want is, this is the induction process. So I said that the likelihood in this form would be very easy to compute. So, which was very, very complicated. You had this entire distribution. So a diffusion model, you were modeling P of x0 to t, or this joint distribution, and you had to really integrate out x1, x2, dot, 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 xt to get p0 of x, right? So, or p of x0, which is the data distribution's likelihood. This is very, very computationally intractable and slow. People do it by sampling and Monte Carlo estimation, but still it's not exact. But in case of in case of flow models, that the likelihood becomes very simple, and I'll show you why it becomes very simple. So we have shown just now. So I said f of I is equal to, or z of I is fi zi minus 1. I have said I've defined this process multiple times now. Now next what I'll do is I'll write down the equation for the PDF. Say I'll write down pz of zi. I'm not writing whatever is the argument of the function, just for simplicity. And I'll write p of, I'm just writing the PDFs, zi minus 1, dou zi minus 1, dou I. This is one of the ways you can write this, right? So where on the other way, this is way 1. And the other way you can write this as, and this is zi minus 1, this means dou fi inverse. So if we are writing it with fi inverse, you can write it this way, with fi inverse, and way 2 is with fi. Right? So what you can do is, you can write z p of zi minus 1 as p of zi dou zi minus 1. So this is with f. So we'll take the second form and we'll see why it will be useful to us. So remember, our goal is to find goal. So here we are seeing we're taking it in terms of fi. So yeah, goal is to find log p of xt, right? Or zt, which is equal to log of p of x, right? So this is our goal. So now let us take log on both sides for this equation. Log of p of z I minus 1 is equal to log of p of z I. And I have plus the log of the determinant of, or the absolute value of the determinant of dou zi, or you can just write fi zi minus 1. This is fi, right? This is fi zi minus 1, right? So I can just take the derivative of the function with respect to the previous random variable, that is zi minus 1, right? So now what I can do is I can write this as P of Zi minus log of P of Zi minus 1 is equal to minus of log of dou Fi dou Zi minus 1. And as soon as you do this, you know this is a difference equation. In your class 11, 12 math, you can just sum over them, right? So you can just say that if you've forgotten, this is like P of Zt minus P of Zt minus 1 is equal to minus log dou Fi dou Zt minus 1 log of P of Zt minus 1 minus log of P of Zt minus 2 is equal to log of dou Fi minus 1 dou Zi minus 2 and so on. So as you do keep doing it, log of P of Z1 minus log of P of Z0 is equal to minus log of dou F1 dou Z0. Right? So as you do it, it's clear now. So this gets cancelled with this, this with this, this with this. Everything gets cancelled. If I add all the t equations or t plus 1 equations or t equations. So you get log of P of Zt or log of x, because Zt is equal to x. This is equal to or minus log of P of Z0, and we said that equal to log of dou F1 dou Z0. Sorry, the right hand side gets summed over all of these, sum over all of these. So I'll get negative of I equal to 1 to, what's the thing? Capital T log of dou Fi dou Zi minus 1. So as soon as I do this, I can write the likelihood of the data, right? Or x is log of P of x Z0, whichever you sampled from. This is your sampling. Whatever you sampled, and this set of Jacobian matrices. So you can interpret and get the intuition in a particular form. I'll show you now. So it's like saying I have some likelihood of noise, right? And whatever determinant I'm going to take, I'm going to increase my likelihood of being in the data distribution. So this is the log likelihood. The PDF is given here. So this is the equation that I have. So the negative of these terms say that how far are the data and noise distribution. Right? What is this entire transformation that you did for? So you know that. So again, if you're forgetting, x is, so it's really not, x is f of t minus 1 and all the way to f of 1 of Z0. So it's going to tell you that starting from Z0, whatever was the likelihood of the data there, of how likely the Z0 point was, and you make all of these transformations. If you have this determinant matrices to be, these values to be very, very high, it means that you're actually gone very away from, so d of f, d of Zi being very high, the derivative being high, is that the rate of change of the function from one random variable to the other is very high, which means that it's quite an unstable process. So this to be high, this term should be low. And this is only low if the FIs make transformations which are very small amounts and takes you towards X. So this is the intuition. So the intuition is like you make small derivatives, and this small derivatives, small Jacobian matrices with small energy is going to give you a larger likelihood of data. So this is so Jacobian matrices with small energy is going to give you larger likelihoods. This was the idea. So what the takeaway message is that you can clearly compute a closed form solution for the likelihood. And now you exactly take a sample, see what is this probability in the data, and you just make all of the transformations. Jacobian matrices are easy to compute, and you just take the log, the sum of the logs, right? So this is also, we have shown that the likelihoods of the data is given by this term. So now what I'll do is, what should be the choice of F? So F, again, I told you, should be easily invertible and bijective. So one of the seminal papers in ICLR 2016 was the real valued non-volume preserving models, or real NVPs. This is a very a flow model. So the originally the trendsetter in the field. So this actually implemented this flow model, saying that, okay, I have this set of functions, that is X is given by f of t minus 1 all the way to f1 of z. So I would want that these are invertible. Invertible, I've been repeating this multiple times, but not only invertible, bijective in a way so that forward process and backward process are the same operations. I will see what I mean by this. So you don't have to compute difficult matrix inverses, which will make it very slow. So what do they say we're going to do? So the idea is make most matrices diagonal, or make them triangular. This is one hope. And the second hope is dfi dxi. The determinant of this should be easy to compute. All the determinants should be easy to compute. And we'll see how did these people do that. Now say we're going to, so this paper said we're going to assume real NVPs said we assume one layer flow model. Flow model where F is going to model from, so you can see the notes above, X is going to model from your data X to Y. X is your noise, and this is your data. So we'll say that f of x is equal to y. So now I'll select a function or f theta, whatever. Real NVPs proposes this one layer flow model. Proposes, what does it propose? Your f theta to be as follows. So say x is some d-dimensional data, right? Capital D-dimensional data. So it could be an image, which 1, 2, dot, 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 till d. So d-dimensional data. I'll say that, okay, if it is a d-dimensional data, for the first 1 to d dimension, say I will take, say this something like this. How do I represent this? Something like this. 1 all the way to small d. I'll just fix it to be y. So the y that I'll have from 1 to d, so this is my x, the noise vector, and this is my y. Okay, I'll say that they're going to be same x1 to d, right? So they'll be exactly copied here, whatever I had. So you could select these d's according to a wish. It's not, you're not mandated to do it in linear order. You could permute them and select the d's, but it depends on the implementation on the models that you'll be selecting. For the rest of the data, I'll say y1 or d plus 1 to d is given by, I'll have two matrices over here. I'll have s theta of, or the exponent of s theta of x1 to d. This is how I'm going to mix it. I'll take a Hadamard product with x d plus 1 to d and add a t theta of x1 to d. This is their transformation, is what they're telling me to do. This is exactly the transformation I need to do. Just look at this. Okay. Let's have a look. So this is what they're going to say. So this is the Hadamard product. What does it mean? So if you're telling me it's a Hadamard product, the dimension of xd plus 1 to d should equal the dimension of s theta of x1 to d. This should equal, these two dimensions must be equal. So how would you do that? So I'll train a neural network. It could be any arbitrary neural network. Say, for example, an MLP. Here, for example, an MLP, which would take, say, 1 all the way to d. I'll mask this out, mask them. This is your s theta or t theta network, and it will give me these values being masked out at d plus 1 all the way to d. Right? So this is s theta or t theta is a transformation from our d-dimensional data to a r t minus d-dimensional data, right? So this is essentially doing a transformation from here to here. So this is just trying to mix the dimensions. That's all we are trying to do, so that there is a link between the data. And we'll see it will become more and more obvious as we do this. And why do I select this as a choice? So first of all, let's take the loss function, right? And as soon as I take the loss function, and then I'll tell you how to train it. So the loss function critically depends on the Jacobian matrix, right? So let's take the Jacobian matrix. So the Jacobian matrix is dou y1, dou x1, dou y2, dou y1, dou x2, dou y3, or pardon me, your x is going to change, and all the way to dou x, dou yd, dou x. Again, dou 1. Right? And then I'll keep doing it. Say I have till d, right? So I'll have dou y d dxd and all the way to d dou y d dou xt. And this matrix, I will not expand it also because this is not required. We'll see why. And I'll say that this is dou y d plus 1 colon d. So this is, we can clearly see this is this matrix, this submatrix that I have over here is a small d cross small d matrix. And this this submatrix that I have over here is a d minus d, clearly. So y's that I'll be taking is from yd plus 1 to, so this is be yd plus 1 and all the way to yd, and a d by d, and this will be d matrix, right? So dx 1 to d, right? So this is what the matrix will be like, small d. The last matrix is going to be very, very interesting, right? So this is my dou d dou y d plus 1 all the way to d dou x d plus 1 all the way to d. And let's try to see what these become. So clearly, dou y1 is just x1, right? So dou y1, dou x1 is equal to 1, dou y2, dou y1, dou x2 equal to dou y1 x3, all the way to dou y1, dou xt are all zeros, right? Because of this equation, right? I'm just taking a partial derivative with any other random variable, just give me zero. So I'll get 1 over here, 0, 0, all the way to 0 over here. Similarly, dou y2, dou x1 is 0, dou y2, dou x2 is equal to 1. And I get all of these to be 0, right? So now you can clearly see up to D, these values are going to be a diagonal 1 matrix. And this matrix will be 0, all 0. So what I can simplify this matrix as an identity matrix, D cross D identity matrix. If you want me to write it in expanded form, this will be something like this. I will have a D cross D identity matrix, 1, 1, 1, 1, 1. This is D cross D. And I'll have a 0, only zeros over here. This is a 0, and this is what is the dimension of this? Yes, so this will be D cross D minus D. Okay. So you can see the rows, number of columns here clearly turn out to be D. Similarly, this I'm not going to expand, and you'll see why. This is difficult to compute and it's cumbersome, so and it will not be required. Now, this term that I have over here, D plus 1, say I'm taking the jth term, right? And I'm taking the derivative with respect to the ith term, where I is greater than I comma j is greater than d plus 1, right? So if I do that, you can clearly see here. So this term does not depend on, so if I write it, I'll just copy this once. Paste. So if you recall, yd plus 1 to d, and if it is greater than d plus 1, so these terms only depend on the xt, and this term is independent of x1 to d, or rather of xd plus 1 to d. And both of these two terms. So these will be just treated as constants. And once I do that, I will just have dou y or dou x j dou xi Hadamard producted with the exponent value of s theta of x1 to d, the jth value plus 0, right? So this does not include I between 1d plus 1 to d. So now you can clearly see this term is equal to 0 if I not equal to j, right? Else, it is very, very simple. Else this is 1. So you can say that dou yj, dou xj is equal to the exponent value of s theta x1 to d, the jth term of this. Clearly, it's very clear, right? So again, if you're not following, so this derivative that I have over here, dxj dxi is equal to 0 if j is not equal to I. Clearly, because say for example, say I write down this equation. So I've already written this here. So say y, where did I write it? Sorry. So yj is equal to x. So you're taking the derivative with respect to yj xi, right? Or yi xj xi I. Okay. Yeah. So this is y. Sorry. So both x. So yj is equal to xi. So if I write this down over here, so okay, this term is exponent of s theta of x1 to d plus d theta of x1 to d. Now if I take a derivative of dyj dxi, I not equal to j, this term goes to 0, this term goes to 0 because these are not, I is greater than d. So this is independent, d theta is independent, this is independent, so this becomes 0. If I equal to j, so then you have yj is equal to exponent of, this is the jth term, sorry. This is the jth term, exponent of s theta of x1 to d, the jth term plus 0. So you can clearly see this matrix becomes exponent of s theta x1 to d 1, exponent of s theta x1 to d2 all the way to the end, right? So this is the diagonal matrix of, so we can write this in cleaner form as, you can see that in the paper as well, they'll write this as I d cross d, 0 d minus d, d cross d minus d, dou y d plus 1 dimension to dth dimension with respect to xi to dth dimension, small d dimension. And you have a diagonal matrix of exponent of s theta of x1 to d. Clearly, if I take the determinant of this is my dy dx, right? So, or this is my df by dz0, f1 by z0, because this is my f, right? f1 converts my x to y. Your y is your data distribution. This is my noise. Good. So that's all I want to do. Once I do that, you can clearly see what is that. This is an upper triangular matrix, or it's a lower triangular matrix with all these zeros. And for any lower triangular matrix, what you can see is, so you can expand across this. So it's a determinant of I d cross d into determinant of diagonal of exponents, right? This is the determinant. And again, these are all positives. These are all greater than 0. It's an exponent term. So this way, no need to take absolutes and so on. So since we know that it's a diagonal matrix, you can just expand 1, 1. And if you have something over here, you can expand over. So once you get this one, you can expand over this matrix, and the rest of the submatrices are cofactor matrices are zeros. And then again, these are zeros. So you can take a expansion over this matrix. Again, it's the product of 1 into 1 into submatrix. And you keep doing it iteratively. And since this matrix itself is a diagonal matrix, again, the determinant of a diagonal matrix, once you reach this, you can just write this as a determinant of these two matrices, which we have already done in detail in matrix algebra. And we can write this as the product of these two determinants, which is 1 into the product of I equal to 1 to d minus d exponent of s theta of x1 to d I. So if I take the log of dy dx, what do you get? You get a summation of I equal to 1 to d minus d s theta x1 to d. Right? So this is going to tell me I'll take this matrix s theta. I'll pass x1 to d. I'll get y. I'll get some transformation s theta of x1 to d in d minus d dimensional space, and I'll just at the end of the day in the loss function I'll just add them. So let's see what does that mean. So our loss function has now simplified. So you may be wondering what is this happening. So I'll just skip these and keep some space and then continue. So our loss function, if you recall, was d of p of y, which is akin to d of px, which was the data distribution in the original equation, minus log of p of z0, which is the noise distribution, and which is in our case log of px under the noise distribution, minus dy dx summation of I equal to 1 to d d fi dou zi minus 1. One to t. This is the equation that we got. Is that? Yes, we got this equation. And if you do that, for our case, this becomes, for NVP, this becomes log of p of y is equal to log of p of x minus, just a moment, yeah, log of p of x minus the summation. So this determinant we just found out was the summation of I equal to 1 to d minus d s theta of x1 to d, and you take the summation over all the outputs, right? Great. So once I get that, so how do I train the model? Train the model. So this is training the model. So training the model is maximizing log likelihood, right? So you'll say that S star is argmax theta log of p theta of y, right? Remember, you only have access to data distribution. Right, you only have access to the data distribution, and this is going to make your life much more simpler. So because you want x as well, and the choice that you have made Remember your x, y1 to d, your f function was y1 to d is equal to x1 to d, and yd plus 1 to d is equal to xd plus 1 to d, exponent of s theta x1 to d, d theta of x1 to d, right? So this was my function, correct? So now this is argmax over theta log of pz comma theta of x minus summation of I equal to d minus d, argmax over theta is theta of x1 to d. Okay, so now you'll tell me, okay, then why do I need the T matrix at all, this the neural network at all? Because when I'm taking the derivative, I'm only taking derivative of s theta. When I'm training the model, this is my loss function, right? This is my loss of theta. So L dl d theta is equal to gradient of log of pz comma theta minus the gradient of theta of s theta, right? So I'll know. Gradient is linear, so I can take gradient and then take the summation. That's fine. But then you'll tell me, why do I need t at all? So I'll tell you, because this depends on x. This depends on x and x depends on t. So let's see how. So x you can see is, so f inverse. So if you want to find f inverse of z or y is equal to x. So you can do that by saying x1 to d is equal to y1 to d, because I'm just copying these equations. They're all equalities. Very good. Next, what I'll do is, I know how to take inverses, right? I know y1 to d is equal to x1 to d. So I'll write the fair one over here. So I'll just do the calculations over here. So see, look at this equation. So y d plus 1 to d minus t theta of x1 to d. And since it's a diagonal matrix, I can again take a Hadamard product of e to the power of, or e to the power of minus s theta of x1 to d. And that is clearly equal to d1 plus 1 to d. So you can clearly see, this is why I was saying, so this is my x1 to d. This is exactly a linear transformation. The same operation that we did for the forward process, we have done for the backward process as well. We've subtracted and we have multiplied our diagonal matrix. So I can say that my xd plus 1 to d is yd plus 1 colon d minus t theta of x1 to d e to the power minus s theta x1 to d. This is my x. So here you see x is a function of f theta inverse y, isn't it? Right? So let us write this down as the gradient of log of pz f theta inverse of y, which is again from data. Say it's an image, minus I equal to 1 to d minus d, gradient of s theta. So you'll see that this acts as a regularizer. And as soon as you see that, you just feel that wow factor. So see, so this term over here, this becomes very, very simple, because P of Z is distributed as normal 0, 1. So I'm saying that what is the likelihood of my data? So P of, so F inverse Y under the normal 0, 1 distribution, right? So this will clearly give me, this is proportional to exponent of f theta inverse y minus 0 squared by 2 into 1, right? So this is all I have. And once soon as I have that, so a log of this is just f theta inverse y squared. Or this is norm squared, right? Because it's vector, so norm squared. Or this is just x norm squared. So my data, so your loss of NVP is f theta inverse y squared, right? Minus summation of s theta of x1 to d I equal to d minus 1. So this is clearly, and you're trying to maximize this. Maximize this. There's a negative sign over here, so this is a negative sign. So you'll try to minimize f theta inverse of y. So this goes to 0, close to 0. So when you make that close to 0, it's like the norm ball around normal 0, 1. So right, so it'll always shrink to 0. So this is a regularizer that makes y close to, or x close to normal 0, 1. This is the beauty of this flow model. So it puts a regularizer by putting, so if you do the math, you find out that you have a regularizer in, and that regularizer trains my s theta and t theta model. And that's how you train it. And once you're able to train it, you will be able to compute the likelihood as well, because x is known, the s theta is known, and you can compute likelihoods for all data points. So, okay. So with that, we come to end of flow-based models and real NVPs. So what I'll do now is I'll show you the implementation of the diffusion model. So again, if you are trying to recall what diffusion models are, diffusion models are nothing but, so you take this x0 vector, the image, and you get xt, the tth noisy version, by using this alpha bar parameter, by skipping all these intermediate steps. So what will I do in my implementation? I will take this schedule. I'll take alpha 0 as a linear schedule. You can other schedules you can look at. Example, sinusoidal schedule, clamped schedule, exponential schedule. A multiple of them, but linear is very, very common, the original schedule that people use. And I remember alphas must be close to 1 for invertibility, because we want the next image to be as close as the previous image. And alpha 1. For alpha end, I want it to be 0.95. So what I'll do is from 0.99, I'll go to 0.95 linearly. And over the time, over the steps. And clearly, if I do that, you can write this as, so they say this is my alpha as a function of time, and this is my alpha 0. This is my alpha capital T, right? So the slope of this line is given by, what is it given by? It's given by alpha T minus alpha 0. That's the height, by T. This is at T minus 1. Because I'm considering we're starting from 1, the 0 is not considered, alpha 0 is not used. So T minus 1, final minus initial. So, and then this is the slope. So alpha T, y is the y equal to mx plus c, right? So, and your t vector is t minus 1, because I'm taking time from 1 itself. At t equal to 1, this is a t equal to 1. At t equal to 1, I'll have it equal to alpha 0. So if at t equal to 1, alpha 1 is equal to alpha 0. And you can just then add alpha 0. So it's just a linear schedule with this sort of a decrease. It's a small decrease, but okay. The denoiser again is will take in a data, will take in a noisy estimate of the data, and will subtract the noise that was added. So it will subtract this noise, right? Once it is able to subtract the noise, I'll show you what the architecture we're going to use. We have talked about sinusoidal embeddings. So what I'm going to do is I'm going to take a UNet. In a UNet, what I'll do is I will take the image, right? I will append sinusoidal embeddings or T embeddings. This is my image. This is my sinusoidal embedding. I will do conv 2D. I'll do a 2D convolution. I'll get a smaller image and then or do max pool. And I'll get a smaller image and a smaller volume, right? And I keep doing this. And see, I will see the implementation in code, but yeah, I keep doing it. And then in the reverse process, what I'll do is I'll take this, I will do conv 2D transpose or upsample followed by conv 2D. They're the same thing. I'll get this and I will concatenate this, whatever I had in the, this is a very, very popular algorithm. So this is from here and this is from here. And then at every step, I will merge them or do conv 2D. I'll get the same volume as before. And this you keep doing unless you get the image. So it's called a UNet because it's like a U. So you start from, so you keep decreasing dimensionality. Dimensionality gives you bottleneck. Then increase dimensionality. Right? You get the final image back. And that's going to be my, so this is going to be my prediction of noise. So we'll write this as the prediction of the noise. Okay. So now with this we've seen how to do this. Let's see it in code. Stop sharing from my tablet. Okay. Just stop sharing here. Okay. So what I'll do now is I'll share from here. Okay. I hope you can see my screen. Just a moment. Yeah. So you can see my screen over here. And this is my code that we have implemented to do that. So again, I'm doing it on the MNIST dataset because I don't want you to be suffering due to camp compute. So what I'll do here is I'll import these libraries. That's fine. And I'll select the GPU and things like that and load the same thing. This is the same thing that I have in the. Okay, let me just. Okay. The same set of codes and I'll just keep this with me. Yeah. So this is my model that I had. Let us see how we implement this conv 2D layer. Okay. Keep it somewhere over here. Okay. So this is my model. So what I'll do is I'll show you how to implement this model. So this is my unit. And this unit takes in an input shape of 28 by 28, and I have a list of filters and number of layers that I've defined. So this is the number of layers that I have over here. And each and corresponding to each of the layers, I have a filter. So these are just design choices, number of filters, number of convolutional layers, and so on. So in one layer, I could have 8, 16, and so on. And I'll say number of filters, that is how many number of filters that I have. Say I have 5 layers and each layer could have like number of filters, number of convolutional filters, say 5, 16, 32, and so on. So what I'll do is I generate the time embedding first. So I already taught you how to do it. So it's the cos of omega t by d and the sine of omega t by d. So for mathematical safety, what we do here is we see what are the omegas over here. The omegas are 1 by t to the power I by d, right? So I have taken, we remember last time t was around 10,000. So what I did was I took this a linear space from say this, look at this. So d equal to d, if d I equal to d, then what do you get this to be? If I equal to d, you get the denominator. So let us just write this down over here. So t to the power of I by d, this is equal to t if I equal to d, if I equal to 0, t to the power I by d equal to 1, right? So I took the log value of this, right? So if you see here, I took the log value from 0 to log of, so I took the log of this. So log of this is nothing but, so if it means the range of for the log is, range for the log is between log t and log 1 equal to 0. That's exactly what I've done. And I've taken 1 increment, and since it has to be in t to the power I by d space, I get it back to exponent. And I do this because of numerical stability. I could have done it directly here, and I would have done away with it. So these are my omegas. And for each omega, I would have this layer of sinusoidal embeddings where I concatenate the omega into t for sine. And so x1 here, x0 is the omega, x1 is time. We'll see how we are going to use it, and we are just going to pass the concatenate time and sine and cos over here. Okay, so simple. And then we have the forward block, as I was saying, the forward convolutional block. So what we do here is we have a conv2d with number of filters, and I'm for implementation purposes, I have kept 2 of them. And once I do that, I have a max pool to reduce the dimensionality. And I return the max pool reduced dimensionality by vector and the convolutional vector, because I want the skip connection at the end. In the reverse transform, what I'll do is I will do the opposite. I'm going to do conv2d transpose. Then I will match size. So I will match when I do conv2d transpose. Often these two may not have the same dimension. So to match the dimension, I will call this layer, which will pad or resize the data as this data, as the input data that I have on the corresponding decreasing or the downweighing layer. Right? And then I'll concatenate these two. See, I'll do that. So what I do is I batch norm them and I do up convolution and I return the up convolution. And you see in the make unit model, what I do is I take the time, I concatenate the time with the input data, the image, and then I do a set of convolutions, and then I do a forward block downsampling blocks, and then I do a set of upsampling blocks. And these are extra convolutional layers that I put for, because these are the people that was there in the original architecture of the paper. And then what you do is in the upsampling block, you're going to get the forward data and you just upsample them, right? You'll just upsample them. And in the upsampling block, just one moment, there you go, you concatenate the input that is from the corresponding skip connection. So you have input skip. So input is coming from the previous conv 2D, and this input skip is coming from the corresponding previous downsampling block, and you're kind of convoluting them, and then you're taking a conv 2D and getting this block here. And you keep doing it, and you say I call a function that makes this model. Say I have 5 layers, which has initially I have only one layer, it's a black and white image. Then I have 8 layers, 16, 32, 64. So you see I have my time proxy. I reshaped it, and I concatenated it with the image vector, which is this. And then I do a bunch of convolutions. I downsampling it, downsample, and with you see the filter size is increasing as I'm going from 16 to 32 and so on. So I've gone to the third layer now, and I'm going to 64. And keep doing it. Now we reach the minimum bottleneck, which is this. And once I reach this bottleneck, I will upsample, and I'll keep upsampling. I'll just see this is going to follow the same pattern of batch normalization, match size. It became 8,8. I matched the size by cropping it. And it's going to continue unless you went and got 28,28. It's the exact same thing. You do a bunch of convolution downwards, and then you concatenate the previous skip connections. You do a matching size, and then you concatenate the skip connection and the conv2D transpose or the upsampling, and then you keep doing convolutions upwards. Now that was the unit that I have the function approximator to predict noise. Okay, so now let us look at the noise schedule. So the noise schedule is very simple. I'll do a dynamic programming approach over here where I'll select alpha t. Again, where did I write this? See, alpha 0 plus 1 I minus 1 by at minus a0 by t minus 1. That's what I have written. I've exactly written down this formula over here, and I'm going to save these, and I'll save the corresponding sigma values, I'll corresponding alpha t bar values, and so on. Once I do that, the loss function is very simple. I pass for every batch here and a set of sample time points, which are sampled over here. I pass it through this xt function, which is going to, what is it going to do? It is going to sample a normal distribution noise, and it'll going to give me the mu, which is the previous image. There's alpha t bar times the data. You can see that this is nothing but this is sqrt of a bar t xt. And sigma t, this is going to be 1 minus of sqrt 1 minus a bar of t. This is what we're going to get. Great. So, and then I'll just add the noise. I'll just do the forward propagation, and the model, the t and the batch will be passed through this, and I'll take the batch, the unit. I will take the noisy sample, and I will pass whatever time embedding was sampled, and this will predict whatever the predicted noise was. This is my actual noise. This is my predicted noise for the corresponding noisy image. And then you can do this. So I exact same loss, weight square by 2. And I'm going to do alpha t minus noise, and I'll do this whole square back propagation. Also, I do the same thing, and I update the weights. I take the gradient of the loss, and I update the weights. I rescale the images between -1 and 1. This is so that the noise is also between -k and k, mostly around -1 and 1, so that the image, it is easier for the model to normalize things, and so you can always keep it 0 and 1. It should still work in principle. I sampled the images. Sampling is, so that was the training. So I trained this model. I take a bunch of images from the training data and pass it through the model, sample the t's, and this is what, and return the loss history. During sampling, what I do is I start from t, I go all the way to 0, and I sample a bunch of z's. So this is my z that I'll be using. This is all the t's corresponding to the number of samples I want for that particular time point, say 500 here, and I'll pass the denoiser, as you know. Where is that? Yeah, there you go. So I will have the weight 1 as 1 by square root alpha t times xt, right? And then I will use the model's prediction of the noise and I'll subtract the noise. Whatever is here has been implemented in W2, alpha t bar, alpha t, and square root of alpha t bar and into alpha t. So this is minus, and then you add the variability term or the novelty term using the z's, which is not sampled from normal 0, 1 distribution. You do it till up to t equal to 2, and the final step, since the variance is not defined for the last step, you just subtract the mean from the model, and that gives you the Langevin dynamics. So we trained the model. We can see the clearly decreasing loss function. It took some couple of hours, 3 hours to train the model, even on MNIST. So I'm not going to retrain it here, but I'll do some inference and show you. So I load the model and say I want to sample 10 images. I'm going to sample those 10 images and I'll show you the Langevin dynamics, what it's actually showing. So that's going to give me. So here I'm plotting the Langevin dynamics and I'll show you what I'm plotting. For your assignment, what I'll do is I'll give you the model most likely, and I'll tell you to do a conditional diffusion. So in conditional diffusion, you can use the same model and use a classifier to predict which class it belongs to. And then you can just keep adding noise and adding that classifier score, as we have seen in the previous class, to this noise's prediction of the model. So see, so nicely it's predicting 1, 2, 3, 4, and so nice generation. So it's slowly denoising across time. And this is one example. So initially noise, random noise, Gaussian noise, and you just denoise it to get ones, and you search denoise to get zeros, denoise to get sevens, fours, 5, 6, 2s, and so on. So this clearly is showing how effectively the model is able to denoise the data. And this is the few generated data, and you can clearly see the quality, the fidelity in which it denoises the data is very, very similar to handwritten digits themselves. It's also trained for, it's a very simple network. You would have trained more complex networks and you'll get better numbers. But yeah. So we'll see. So these are visual inspections. In the future, we'll see how to actually quantify these using FID scores. When we'll do GANs, we'll see that. But more or less, this is the idea of the implementation of diffusion models. So I'll give you the code. Please play around with it. So it's completely implemented by me, and then just plug in the terms. And if you have access to compute, change a few things here and there and train the model, maybe change the unit, use a transformer and so on. So with that, I'll come to the end of today's session. And if you have any questions regarding the implementation or the flow models, you can come back to me and write it in the chat. And then I'll be happy to discuss it with you. And what I'll do next day is I'll be discussing energy-based models, and in energy-based models is we'll see how score functions have been effectively used in energy-based models to train them. So that's the plan, and that will be session 7, and then we'll slowly get into adversarial neural networks or adversarial generative models. And with that, we'll come to the end of today's session. I'll stop recording.